Welcome to Kitchen Table Electronics, lesson 4.3, the last lesson in this module on transistor circuits. So I'm being a little archaic here because transistors are almost things of a bygone age, but they are very easy to play with and illustrate a lot of the difficulties you encounter in more complicated circuits. And they form the basis, together with field effect transistors, of which more later, of operational amplifiers, which is something you will use quite a lot. So by understanding transistors, you get a feel for other circuit components. The topics I'm going to cover are biasing a transistor so it can operate in that linear region we looked at before when we traced our VCE versus IB. How to design a given gain for a transistor amplifier, and we're going to look at the output and input impedance when we use this, in particular when we design the biasing circuit and then make an amplifier from the transistor. So here's the circuit we used to measure the collector voltage versus the base current. We would like to be able to sit this transistor at a point where this VC was about half of this. In other words, if it's 5 volts, we'd like this point to be at about 2.5 volts, so that as we amplify a signal on the base, it can go up and down between the largest possible range. If it was stuck up at 5 volts, it would only be able to go down. So if it was down at 0, it would only be able to go up. So you want to sit this somewhere in the middle. But how do we choose a bias value if this HFE parameter is so variable? Just as bad as that problem is the fact that this voltage between the base and emitter when this diode is turned on is, as I pointed out earlier, not a constant. It's quite variable from device to device. It depends on temperature, and your circuit is just not going to be stable if your base current has to depend on a constant value of VBE. The answer to these problems is something called negative feedback using an emitter resistor. So in other words, we reduce the gain of our circuit deliberately by putting a resistor in the emitter lead. So we're going to go ahead and make this circuit, and we'll understand it fully after we've done some measurements on it. But let's just go ahead and put it together. So here's our 1 kilo ohm in the collector lead still. Notice we've now put 470 ohms, here's the color code for it, in the emitter. So here's 470 ohms from emitter to ground. Now we've done something rather special with the base. We put a voltage divider between the plus 5 volts rail and ground, consisting of a 4.7 kilo ohm resistor here and a 2.2 kilo ohm resistor here, and that now sets a voltage at this point. So go ahead and make this circuit. Here is the Fritzing pretty layout, and here is the real layout on my kitchen tabletop. And these two leads then are just the plus 5 and ground connections on my Arduino board. Even although this is a very simple circuit, please go ahead and put your ohm meter between here and here and make sure there isn't a short, because you don't want to have to be running out buying a new Arduino in the middle of this course. Okay, I made this circuit and I applied power, and then I just put one of my voltmeter leads on the ground and measured the voltage at all these points. So across this emitter resistor, I got this 0.8 volts. I had about 3 volts at the collector here. I had about 5 volts, of course, as I knew up here, and about 1.5 volts on the base. We can actually deduce quite a bit from these measurements, so let's go ahead and do that. So what is the voltage between the base and the emitter? Well, it's this voltage minus this voltage, and so 1.54 minus 0.83 is, near as damn it, 0.7 volts. Exactly the forward bias voltage drop we would expect for a turned on diode. So by biasing the base positive of the emitter, this junction is turned on. Now we have 0.83 volts across this 470 ohm resistor. That is, here we are, that gives me a current, emitter current, of 1.77 milliamps. We have 4.91 volts minus 3.14 volts across this 1 kilo ohm resistor here, and that gives me a collector current of 1.77 milliamps. Look at that. The collector current equals the emitter current. And so as a matter of experimental fact, this tells you that the current in or out of the base must be essentially zero, as we would expect to be for a high gain transistor. It's still not completely obvious why. We have to look at the circuit in a little bit more detail, which we will on the next slide. But just to summarize, this now leaves this transistor biased on with about 0.7 volts drop between the base and emitter, and a collector current equal to an emitter current of about 2 milliamps, close to, which, by the way, 2 milliamps and 1 kilo ohm is going to be about a 2 volt drop across this resistor, in fact 1.77 volts, as we wanted in order to set this point about halfway between here and 0. So we've achieved that goal. Okay, the base voltage. Let's take a look at what that is. Let's assume, as is justified by the fact that the emitter and collector currents are essentially equal, so really no currents flowing in or out of this point, none that we can measure anyway. Let's assume that IB is 0. If IB is 0, then this is a very simple voltage divider circuit as we covered in class 2. And so here is the equation for the voltage divider circuit. This voltage here is 2.2K divided by 4.7 plus 2.2K. And that times 4.91 volts is 1.56 volts, which is essentially equal to the 1.54 volts we measured here. So this base voltage is determined by this voltage divider, and it doesn't care that there is a transistor hung off it. So you can see something rather miraculous happening. We have fixed this voltage with a voltage divider that says, I don't care if there is a transistor here. This forward voltage drop is fixed by the physics of the diode, so that fixes the voltage here, which in turn fixes the current through this resistor. Once you fix the current through this resistor, knowing I equals IC, you fix the current through this, and so you now have a stable operating point for this transistor determined by this voltage divider. What makes the voltage divider so robust and not sensitive to having a transistor here? If I replace these by much larger resistors, this would not be true anymore. Well, let's take a look at that. The current through the base here is going to be the emitter current divided by the current gain of the transistor, which is about 100. So if I apply a small voltage increase to the base, it will appear on the emitter. However, the current taken by the base is going to be just 1/100th of the current flowing through here, because that's what the current gain is. So it'll be the emitter current divided by 100. So the effective resistance or input impedance, I'm going to use this word and explain more in the coming class, of the base then, is going to be this change in voltage divided by this change in current, which is HFE times the voltage change across the base divided by the current through the emitter. So I've used my HFE here to get the emitter current. So it's about HFE times this resistor. So in other words, I've increased the impedance looking into the transistor by a factor HFE. So if this is 470 ohms, and I have a current gain of 100, it looks like 47 kilo ohms looking into the base of the transistor. So let's look at some equivalent circuits here. Here is my voltage divider and here is the transistor. I've just said we can replace the transistor with something like a 47 kilo ohm resistor, and here it is. Now we know we can replace these two resistors with their Thevenin equivalent circuit. Instead of 5 volts here, we now have a 1.54 volts voltage source, and then the Thevenin equivalent resistance of these two resistors. And from lesson 2.1, you will agilely remember that that looks like the combination of these two resistors in parallel, or R2 times R5 divided by R2 plus R5. And here we go. We put the numbers in 4.7 kilo ohms, 2.2 kilo ohms, and we get 1.5 kilo ohms which is much less than 47 kiloohms. So in other words, this voltage divider really doesn't mind being loaded up by the transistor. And actually the measured voltage here is very slightly less than the calculated voltage, probably within the error of our cheap meter, but nonetheless showing you that some current is taken through here, but not a lot. Now, you might ask, how did that circuit end up working so nicely? Well, that's because I designed it that way. What did I actually do? I didn't work backwards from a working circuit. I decided first on a quiescent current, a reasonable current for the transistor turned on. You can get that from the data sheet, and I chose a couple of milliamps. I picked a emitter voltage to be greater than VBE. Why? I didn't want small changes in VBE to be significant, and so I want the emitter to sit at a significant voltage, which then determines the emitter current and makes VBE less important. So I chose a voltage that was a volt or so, which then determined, of course, given the current through the transistor, determined the value of that resistor. I then choose a resistor value close to that. You'll find that you'll never get the resistor values you calculate on your calculator, but because these circuits are so robust, you don't have to be too precise. The feedback from the emitter resistor guarantees this will operate as you want it to. I chose the collector resistor to drop about half of V plus minus the emitter voltage. I then estimated the base resistance from HFE times the emitter resistance. This then determined a Thevenin value by saying I wanted to have it being about 10 times this base resistance. Wait a minute, am I showing it as C base? Yeah, it is C base divided by 10. I'm sorry. I want it to be much less than the base input resistance, so you're not loading it significantly. And then knowing that I want the base voltage to be the emitter voltage plus 0.7 of a volt, I have one variable, which is the base voltage. I have a second, which is the Thevenin equivalent. And I have a pair of simultaneous equations to solve. And from that, I determine the values of R2 and R5. Okay, let's make an amplifier. At this stage in the course, we do not have ourselves a nice variable signal source, so we're going to cheat and take the signal that's available on your O1 scope. If you look at the right-hand side of the front panel, you see two little pins here, and this is the calibration output that you can use to check that your scope's working of a square wave of 5 volts at 1 kilohertz frequency. It's pretty accurate. So what we're going to do is we need a ground connection. We could connect this pin to ground on the circuit board, but we're going to use our scope probes, and either one of the two will have a ground connection. So we don't need an extra ground connection, but we're going to run a wire from the scope through to a potentiometer. Why a potentiometer to ground? Well, this is 5 volts, and since we've only got 5 volts here, we want to reduce the signal to see that we can amplify it. So we're going to use this potentiometer here with a slider set down here somewhere to reduce this square wave signal. Now, secondly, we can't just apply this lead straight to the base of the transistor. If we do that, we'll short out this voltage divider. To couple the AC signal to the transistor without shorting out this voltage divider, we use a capacitor. We haven't studied capacitors yet. That is for the next section of the class. But in brief, a capacitor blocks DC and passes AC, and so we're using quite a large value of capacitor. This is called an electrolytic capacitor, and you'll see what they look like in the next section. And so this then is our first go at an amplifier. Here's that polarized electrolytic capacitor. They label the negative side rather than the positive side for some reason. So this gray stripe with this sort of minus symbol and arrows pointing towards it says this is the negative lead, the other side's the positive lead. It matters because these capacitors are made by using electrochemistry to make an oxide film on an aluminum foil. And if you put them in the wrong way, you'll decompose the oxide film and the capacitor will short and go bang. All right, so here we go. Here's our potentiometer. Here's the top lead, and this is from lesson 2. It's still got the wires on it, connected to the O1 oscilloscope, 5 volt, 1 kilohertz signal. the other side of the potentiometer to ground, and the wiper here going to this 4.7 microfarad capacitor, which goes onto the base of the transistor. I have got channel 2 connected to this wiper of the potentiometer to see what signal I'm putting in, and I've got channel 1 here connected to the collector, and my channel 2 probe ground clip is connected here, so that provides a ground for channel 1 and for the 5-volt signal. All right, here's what I get on my O1 scope. The red trace is channel 1, the output. The yellow trace is channel 2, the input. They're both on 1 volt per division. The nice thing is I don't have to strain too hard to measure because my scope tells me what the peak-to-peak voltages are. I have 3.32 for channel 1 and 1.72 for channel 2. The ratio of the two is about 2, so that's the voltage gain of this circuit. Why? Okay, let's take a look at it. Remember that if I put a delta V on here, I'm going to get the same delta V here, and this is going to cause a change in current, which is delta V divided by R3. So here's the change in current. The emitter current equals the collector current, so I'm going to see a similar change in the collector current. And so if I now ask what the change of VC is, so VC is actually going to fall if this goes up, there's a 180-degree phase shift, it's going to be this change here now divided by this change here times the change in IC times R1, and therefore it's going to be the change at VB times R1 divided by R3. And so the gain, which is delta VC over delta VB, and I'm not putting a minus sign in because VB is actually falling as VB rises, so I should strictly put a minus sign in there, is the ratio of R1 to R3, or 1 kilo ohm to a half kilo ohm. It's 2. So the circuit is behaving exactly like we want it to, and it's giving us a gain set by this resistor to this resistor. Now you can see that if I made the emitter resistor even bigger, the gain would fall. And this is what I mean by negative feedback. We're reducing the gain to make the transistor more stable. What can we do to increase the AC gain of the circuit? We can play a trick. Remember I told you that capacitors will not pass DC, so I can make the transistor quite stable at DC if I put a capacitor here. Notice I've got the plus sign up here now on this capacitor. But they do short out AC. So for a small AC delta V here, instead of seeing this emitter resistor, I see a short circuit through this capacitor. So adding this capacitor should increase the gain of the circuit. Here it is. I've now put this capacitor between the emitter and ground. What happens? And look at this. I've now had to turn my potentiometer all the way down. In fact, I can't turn it any further down. And I'm actually getting 4 volts, which if you think about it is the maximum I can at the emitter. The gain then, as far as I can tell from this measurement, and you'll see the catch in a minute, is this 4 volts divided by the 0.6 volts I'm putting in, which is about 7. So why is the gain not infinity? Well, actually, there's a very good reason here, which we'll come to in just a second. But let's just take a look at what happens if RE is shorted out. It turns out there is still a resistance associated with that diode between the base and emitter. And in fact, if we plot the emitter current as a function of the base emitter voltage, I put the collector current here, but collector and emitter current are the same. The derivative of this, the slope of this, is, of course, the resistance of that diode in effect. Now, because this is an exponential, it's not constant. Remember, the derivative of an exponential is I'm going to get the function returned again, which itself was exponential. When I do the math, what I get is that the emitter resistance is 25 ohms divided by the emitter current in milliamps. So I had 1.77 milliamps for the emitter current, and that means if I divide 25 ohms by 1.77 milliamps, I get 14 ohms. So my gain then should be the ratio of this 14 ohms, should be the ratio of 1 kilo ohm to this 14 ohms. It should be 71. It's about a tenth of this. Why? Because I'm not measuring properly. I couldn't turn my potentiometer any further. And so in fact, it turns out when I played with the potentiometer, I saw that 4-volt output simply didn't change. It's just the maximum possible output. It is just the 4.91 volts minus the emitter voltage minus the VCE sat, and that is about 4 volts. So I'm just saturating my amplifier. So it's showing you that it's working. We're driving it in a silly way, so we don't really measure what its real gain is. Its real gain, though, could be as high as 70. Okay, so we now, I think, understand transistors pretty well. One last thing I want to say is, as I said at the beginning, you wouldn't actually make yourself an amplifier from a transistor these days. You can use an operational amplifier. If you want to, here is a schematic for making an amplifier. I think I've got what did I have? A 20 times with the choice here of R2 is 1 kilo ohm and R1 is 20 kilo ohms. So you can for yourself work out why the gain would be 20. I'm using a capacitor to couple in. Why? Because I've had to set this point at 2.5 volts, so this point is at 2.5 volts with no input. And I do that by setting the non-inverting terminal of the op-amp to 2.5 volts with a pair of 10 kilo ohm resistors here. Why have I done that? Well, this is because I'm using a one-sided voltage supply. And so to make this an amplifier, just as I had to bias the transistor at halfway between the rails, I have to bias this at halfway between the rails. If you have 2 power supplies available, which is a real pain to organize, but if you do, you'll see in the literature that most op-amps actually operate with this point at 0 volts and then a plus and a minus supply. But that's a hassle and would stop us using our Arduino power supply. So here's an amplifier you can build if you want to. Now, I've introduced a lot of terms in this section, like telling you what a capacitor does and telling you, using the word impedance when you know I sort of mean resistance. And at this point, if you're confused, good. I've actually been a very bad addle-headed teacher by using those words, but those words are very commonly used. You're going to get a rigorous meaning for them in the next and final section of the class.